Okay, so in this lab, you will basically not write any code because I have provided the code. We're going to be using the same code I covered in class, the one that we used in ADC to control the dim or how dim is an LED in here. Okay, so but instead of the LED, actually in addition to the LED, what we're going to be doing is I connected a DC motor in here, and this DC motor that I have is a 5-volt one. It's just basically a computer fan. You probably can see it. Okay, so 5 volt. What I did is basically I took it has 3 wires. Your DC motor might not have 3 wires. The third wire is a measurement because it is for a computer fan, so you can see how fast it is. We will not use that particular one in here, so we're just gonna throw it out. And what we will be doing is we will be controlling the speed of this motor, this DC motor, using or the fan using the same technique, basically pulse width modulation. Code from a code perspective, I'm not hiding the code because you already have it. It's the same exact code. There's no difference whatsoever. Not even the frequency, not even anything. We're just going to operate at the 1 kilohertz, and that should be fine for this type of motor too. Okay, so but what you need to do is you're going to see that there are a few ways to connect the motor to my microcontroller. Of course, you can directly control it with the pulse width modulation. However, that's a bad idea because these motors they draw a lot of power, and it might draw too much current for your microcontroller to handle, and at that point you will be burning your microcontroller, or you're going to maybe ruin it or something. So what you usually do is you power it from a different power source. Okay, you power it from a different power source and you isolate it from your microcontroller, and the pulse width modulation signal will be the thing that you control the speed with. So let me explain. So the lab manual has a certain circuit, but I came up with a different circuit actually. I found online and I modified it a little bit. So this circuit we're going to be doing is this is my microcontroller. We're going to take the pulse width modulation output, which is currently connected to the LED. I'm just going to basically take another wire. It's exactly the same. I'm going to pass it through some sort of a resistor. I believe I'm using the 330 ohm here. It doesn't really matter. Something not too big, not too small. Okay, 330 ohms is fine. That's what I have because I used it with the other LEDs. And then what I did is I brought a transistor. I just basically have one transistor at home, and it just happened to be the 9013. Okay, I did not care which transistor it is, but it's just a BGAT. It's just one of these BJT with I forgot what's like. Anyway, it's just a BJT transistor that I have. Okay, so now I connected the base to the pulse width modulation, and then I connected the emitter to the ground. And instead of just connecting the collector directly to the 5 volts, because this particular motor is operational at 5 volts, your motor might be operational at a different voltage level. So you're going to have to look up what you have as a motor. So I just basically connected that motor in series between the 5 volt and the emitter or the collector of the transistor. Okay, so here is basically just a diode, and this diode is just as a protection mechanism so that the DC motor doesn't push like current in the opposite direction or not. Because remember, it has like coils and whatnot inside it. In addition, I found out that because the power supply I'm using is actually the one that came with the analog discovery, and if you read the specification here, it tells you it allows only 500 milliwatts total or 700 milliamps per output per channel. I'm only using the positive channel for 5 volts. Okay, so technically you're gonna have to figure out what your power supply is capable of and whatnot. And I found out that my power supply is just capable of running this particular fan. And the fan I have here, when I flip it, I don't know if you can see it, if it's in focus and on the camera, you're going to see that it's operational at 5 volts, and it can draw up to 0.15 amps, which is basically 150 milliamps. So 150 milliamps is less than 700 milliamps, and I'm assuming the microcontroller is not going to draw that much anyway, so it should be able to handle this particular motor. Other motors might be completely different. However, you will see that what I did in here is I connected it on a smaller breadboard. It's just easier for me than dealing with these wires. I just basically kind of permanently connected, not permanently, but connected them here, and I basically took these wires because I was testing it around. Okay, so you do see the LED here, but what happened is whenever I turned it on, every now and then, whenever this motor just starts, you're going to see that it spikes, the voltage spikes a little bit, and because the voltage spikes and the current spikes as well, I see that my protection in this power supply just turns off because it exceeds it. So my solution was I just basically connected a capacitor in parallel. So you have this is pretty much my circuit. What I did is I added another capacitor in parallel here, and that capacitor just served as a filter. So whenever there's a spike, actually you can't have that like really huge spikes up and down, and that triggers the protection mechanism of my power supply. Okay, so you might have to use that capacitor, you might not, depending on which power supply you have. Mine could not, so I just connected that capacitor there. Okay. So let me just talk about what's happening in here. The pulse width modulation, if you guys remember, it's just basically as if I'm applying some voltage between 0 all the way to, let's say, 5 volts. And it's just basically turning on and off that particular transistor, or pretty much you're controlling the DC motor. I'm controlling how much voltage does it have on it. So let me just show you how it actually operates. So what I did in here is I did put some sort of like tape here so that you get to see it, like to get to see the speed. So and I kept the LED so that I get to know that my microcontroller is on, because my power supply kept tripping off and I didn't know, and I was like, why isn't it working? Why isn't it working? And I realized that my power supply was off. So I kept the LED on, and I don't know if you can hear it, but I can hear the hum of the motor. It's not working yet, but it's getting there. So I'm gonna keep moving, keep moving, keep moving, keep moving. I'm doing it slowly so you get to see. Yeah, it started to move. And there you go. Come on. Okay. Yeah, it started to move. It's like I'm just doing it really, really slowly. So now it's one of the slowest I can actually get. And of course I can push it all the way through, all the way through, all the way through, all the way through, all the way to the other direction. And that's basically the fastest speed it can get. And that's pretty much it. Okay, so the directions that came, or that I posted on Blackboard for this particular circuit, came with a different isolation mechanism to isolate the motor from the pulse width modulation. Let me just open that file and talk about it. All right, so the instruction that came with the lab is basically offering a little bit of a different isolation mechanism, and the isolation is optical. Instead of using just a transistor, we use some sort of a like an LED and a photoresistor or phototransistor, sorry, and it will create some sort of an isolation. So you're operating at 5 volts in here, and in this particular case, it's showing 12 volts because the motor, they assumed the motor of 12 volts. Mine was 5. Now what happened is I tried to use this particular circuit. I do have the optocoupler, but I don't have a motor that operates at 12 volts. So I operated at 5 volts, and it took me a few hours to figure out why it wasn't working. So whenever I connected it in this particular configuration, whether I put the motor in series with the emitter or the collector, it didn't actually work. The maximum voltage drop across that motor was basically 2.7, 2.8 volts. And when I tested it on an analog voltage, that motor started working when I put about 3 volts all the way to 5 volts. So it wasn't working, it wasn't even moving. And it took me a while to figure out, was it my circuit? Was it my code? It wasn't definitely the code, because I tested it. It's just like the voltage drop was crazy. I added resistors, I did everything, but the only thing I didn't do is actually to go and really read the data sheet of this particular optocoupler. So after I figured out everything, I was like, okay, let me do read that data sheet. And the data sheet, what's most important is actually the output. So you can see that the collector current, that's actually, or the emitter current, the collector peak current. So basically the maximum current that you can get from that 12 volts, in my case at 5 volts, all the way through, because remember, it's like that current is almost, because the current coming from the base is almost nothing. So the current that you can draw here, if you take a look at that, the peak current is 100 milliamp. So if you flip that particular motor that I have in here, and if you guys remember a few minutes ago, I mentioned that it was 0.15 amp, which is 150 milliamps. So there's a 50 milliamp difference, and that's basically what created it. I spent a few hours just to figure this out. But this particular, because I'm operating at a 5 volts, and the maximum you can get is 100 milliamp. If you think about it, that's basically half a watt. So your motor should be just operational at half a watt. I don't know if there's a motor that operates at a half a watt or whatnot. Maybe something like this. I do have like a couple of motors that might operate at this. Like one of them is that, which is super tiny, but it's like it was so annoying to deal with that I didn't want to. It's like really small and I couldn't get it to the breadboard. Like I had it to solder and do stuff, so I didn't want to do it. But anyway, so you can use optocoupler if you choose to because you have it. Like if you have a motor that needs 12 volts, you're gonna have to figure out a power supply that gives you 12 volts. In the 12 volt case, it might work because 12 times 0.1 is 1.2 watts. So it might work. A 1 watt like motor is reasonable, but in my case, it didn't work because I couldn't draw that 150 milliamp for the maximum speed I need. Okay, so something to think about. This is why I basically selected not to use the optocoupler. I just basically used the transistor. In any case, I don't think there's a major difference between these two cases. Well, it will work with the 5 volts if your motor is operational at 5 volts. Okay, so what I needed to do is basically take that code and just connect everything and make sure that the motor is working, because you will need that motor to you will need that motor for the final exam. You will be controlling the speed of a motor or final exam. And remember, you might need to connect the capacitor in here. I just left it off because it's not necessary, but it just basically protects you from spikes in the current and voltage that the motor might actually trigger.